So the last speaker today is Simone Paradiso, and he will be talking about cosmological parameters.
Hi all, and have a good morning, good evening, or whatever it is in your place. So my talk will be about CMB analysis, so with end-to-end error propagation, like Loris. It just naturally follows that his talk. And the focus here is on likelihood and cosmological parameters. So my name is Simone Paradiso, and I'm a PhD student in Milan. So without spending too much time on this, I just want to recall what Loris already mentioned, and in particular, what is the BeyondPlanck main processing. This is all about solving this equation where we have two terms, one that is including all the data parameters, data model parameters, and another one that is basically a special priors that for CMB is just simply the covariance matrix of the CLs. What we actually use for extracting cosmological information from our dataset is a low resolution resampling step process. That this kind of low resolution resampling, Loris already described it, is performed full sky, preserving only low sampling only low multiples, and providing us with 40,000 CMB samples, low resolution. We resample the CMB map set and site 32. Moreover, we have a high resolution resampling, also discussed, that's providing us with 900 CMB sample at full resolution this time, and applying a spatial priors, so this S becomes different from zero, so we're exploiting all the information we have from the CMB distribution in the spatial distribution. So we are provided a set of samples drawn from the full data distribution, including all the propagation noise of all the data parameters. So we have complete end-to-end uncertainty propagation throughout the pipeline of the sample parameters. Now let's move to the likelihood itself for BeyondPlanck. So we have an overall coverage of the multiples from L equal 2 to 600 when talking about temperature, and we gather information from polarization in the multiple range 2, 8. The likelihood that you will see discussed in the upcoming paper is actually using only E modes and cross correlation with temperature. But in this paper and in general within BeyondPlanck, for consistency checks, we use also the B modes, of course. And as has been done in Planck and WMAP, we divided likelihood into two likelihood themselves. So we have like a low L pixel-based likelihood that is exploiting, that is using, so this performing this slow operation in real space, so exploiting the full dense noise covariance matrix built on samples. We'll see how we build this noise covariance matrix. And as already has been said by Loris and Hans Christian yesterday, it is basically a Gaussian likelihood as function of this of the signal within each pixel, and a higher likelihood that is actually based upon the fast operations in harmonic space, and is based upon the Gaussianized Blackwell-Rao estimator on temperature and in the multiple range from 9 to 600. So let's start from the low L likelihood. As I've already mentioned, the low L likelihood is based upon the direct CMB map and noise covariance matrix from the 40,000 samples, resolution samples. So we have the signal, the SCMB, so the signal that is the ensemble average of the whole sample, the whole sample set, resample set, and the noise covariance matrix is what we usually call the sample-based covariance matrix. Is built from the resampled low resolution samples. What we furthermore do is a Carrier-Loeb compression to isolate only significant modes. What's significant? Well, we basically filter out low signal to noise eigenmodes from the input data. We impose a threshold of 10 to the minus 6 in this sense on the eigenvalues of the decomposed input map. And we also apply a threshold in terms of multiple. So we stop at L threshold equal to 8. So we are basically filtering out the modes that don't carry information in this sense, and we are also stopping our likelihood up to L equal 8. On the right, you can see what we call the Whitenet CMB map. You already saw this in Hans Christian presentation yesterday. In this map, you should see a Gaussian vanishing mean with the unity standard deviation field where we are noise dominated. And of course, this map, except for the mask that's covering the galactic plane, is basically noise dominated. Even though we can see some excess, some signal that might be some excess of power, the very focal point here is that we don't see evidence of residual foregrounds outside the galactic mask. This is instead, you already saw this as well, this is instead a slice through the noise covariance matrix. Here on the top right, there is a pixel, the 100 pixel, and what you see elsewhere is just the correlation of this pixel with all the other pixels. So we are basically plotting here the sigma I, sigma j, keeping I fixed to 100 and j spanning throughout the pixels from the Q and U maps. And of course, appears the correlation, a negative correlation in the galactic plane, some structures that are more likely related to some systematic residuals. And moving to the likelihood himself, let's just point out some interesting features here. The first question we might ask ourselves is, since it's basically based upon samples, how many samples do we require? Well, we have plotted here the optical depth of ionization estimate, so tau as function of the number of samples we produce during the low resolution resampling step. As you can see, we are moving toward a plateau after some burning period here. And the point is that we have, with 40,000 samples, we are just at the very beginning of such plateau. Of course, we don't want to stop here. We would like to have more samples in the future, like something like 2 or 3 times what we have now. But we can assess that we are safely we have reached some convergency in this optical depth of ionization estimate with this number of samples. By other hand, if we move to this plot on the bottom right, here is a comparison of the posterior distribution of tau with respect to other experiments, and you can see that there are 2 BeyondPlanck posterior distributions, where we have a full sky one that is not actually full sky, but this just means that we are covering only the galactic plane, so corresponds to about 72% of the sky. And in this case, we have a huge bias in the tau estimates. And this is basically can be explained in terms of chi-square. We have a chi-square of 10 to the minus 4, and this means that we have a very poor fit. So our data don't fit with the lambda CDM model. So whether the lambda CDM models is wrong, or our data includes a lot of unresolved systematics that we are taking into account during the analysis. So what we do is to move to this other curve that is based upon the same galactic mask, but also removing the southern hemisphere. By removing the southern hemisphere, so keeping only the northern hemisphere and removing also the galactic plane, we see that we have an excess of chi-squared of 16%. This is totally acceptable. And with this sky fraction, it is about 32%. We see that also the estimate of R is stable at this level, and also the optical depth of ionization estimate of tau is consistent within many experiments and is also stable at this level. So what we do here is what we do in BeyondPlanck is focusing on the northern hemisphere, and this is the mask we use for producing the likelihood input. A last consistency checks, actually a stability test has been done to assess the ideal multiple range. So we already mentioned that we stop at L equal 8 for the lower likelihood, but we tested the likelihood within 2.8 and 3.8 as multiple range. But we basically see that the posterior distribution are identical. So also the chi-square is identical. This is 16% of probability of excess, and the tau estimate is estimate itself. So we use the larger interval we can. So 2.8 will be the lower likelihood BeyondPlanck application for. Let's now move on and talk about the higher likelihood. We apply a Gaussianized Black-Rao estimator-based likelihood on the 900 high resolution resampled CMB maps. For details about this Gaussianized Black-Rao likelihood, you can refer to this paper here. And we use this likelihood only for temperature because the Black-Rao estimator is suffers in case of suffers of poor convergence in case of low signal to noise ratio, and with polarization we have a very low signal to noise ratio already at multiples greater than 10. So what is a Black-Rao estimator? On the right we have a figure, a plot that is giving what is the intuition behind this approach. So we can construct the probability of the CLs given the observed sky. So sigma Li is nothing but the full sky power spectrum of the sample I, and we can construct this probability and just average over all the samples. So the average of all the probability will be our Black-Rao estimator. What we do for getting faster convergency is to move into Gaussianized variables. So we apply a Gaussianized Black-Rao estimator, is constructed, and this is by applying this Jacobian transform. This is the Jacobian of the transformation. So we are moving into XLs that are by definition Gaussianized variable in the sense that those are the distribution of these X's are Gaussian, as you can see here. So moving into this space, we construct the Gaussianized Black-Rao estimator on which we build our higher likelihood. Just stressing something that Loris already shown. Here there is a plot of the values of the observed power spectra at L equal 200, 600, and 800 from 6 independent chains as function of the iteration number, the sample number. These are just 60 samples. We've produced 150 for each chain, but it's just to show that for L equal 2 and 200, we have basically null correlation length. So there is a very high mixing for sequence samples, and this is actually telling us that we are probing the whole posterior distribution quite efficiently with a low number of samples. At L600, we still see a good convergence, even though there is a longer correlation length, and things start to be worrying at L800. We see an even longer correlation length. This is just, of course, an illustration, but if we look at the German Rabbin statistics, thanks to Loris he already showed it in the previous talk, but just to mention again, the fact that at up to L700, we have a good convergency from the German Rubin statistics. This should be, when we are close to 1.1, we are fine with, we can assess convergency quite safely. And in our case, so we take L equals 600 to be quite sure that we are in a good convergence regime. So this is the safe choice, conservative choice. Moreover, a stability check has been made comparing the high likelihood application up to L600 and 400, propagating it up to the cosmological parameter estimates. And we see that the true configuration gives constraints that are compatible within 1 sigma. So we are fine with this. And this is a plot showing on the top the CLs constructed from the Gaussianized Blackwell-Rao estimator. So the black solid line are these CLs compared with the Planck and WMAP power spectra, estimated power spectra, and the dashed line is a lambda CDM reference model that is basically the Planck 2018 best fit. On the middle panel, you see the relative difference with respect to this reference model. And on the bottom panel, you see the percentage of this difference. And now move to likelihood results, so numbers. What I want to show you here is basically the difference with respect to Planck at first, and show that we are pretty much fully compatible with Planck 2018 results. I show you here BeyondPlanck's, where beneath L600 is the only BeyondPlanck, so low L plus high L likelihood. But also I provide here run adding information from L600 to 2500 using Planck IL TT likelihood. And you can see, of course, here, as I mentioned, that as I said, you see that we are fully compatible with Planck 2018 results. By other hand, we have larger errors, but this is the major contribution to these larger uncertainties comes from the fact that we are using only LFI and WMAP. So we are not using H5 channels for estimating these parameters. Moreover, there is also a run adding lensing and BAO to be consistent on what has been done within Planck. So nothing but showing that it is possible to do that. We did it. And here comes the focus of this whole presentation to me. I think this is quite interesting. We want to show what do we mean with end-to-end error propagation, and what is the effect of this error propagation at the cosmological parameter level. So to show the impact of parameter estimation from these uncertainties propagated throughout the pipeline, I use the low L likelihood. We use the low L likelihood and the estimate of tau as benchmark. This because tau is highly sensitive to systematics in the maps, so in the data, so it's a good benchmark in this sense. What you see here, the black line, is the posterior distribution as estimated from BeyondPlanck low L likelihood. So you can see the legend. These are the set of parameters we are marginalizing on. So in BeyondPlanck, within BeyondPlanck, as you already understood from all the talks so far, we marginalized over TOD parameters, foreground parameters, and white noise. We performed also 3 more runs, low resolution resampling runs, marginalizing over just only foregrounds and white noise, TOD and white noise, and only white noise. What does it mean? This means that basically when we perform these resampling runs, just kept once the foreground, once the TOD, so the frequency maps, and one time both these datasets as fixed to one initial value, and we didn't update these values throughout the resampling procedure. So what we want to compare and on what we want to focus on is on the uncertainty. The difference on uncertainty that comes from the run in which we marginalize over white noise only, so the blue line, and the run in which we marginalize over the whole data parameters, so TOD, foregrounds, white noise. Foregrounds plus white noise coupling leads to non-marginalizing over these 2 set of parameters, leads to, of course, to lower uncertainties, but within the BeyondPlanck frameworks, it will lead to underestimation of our uncertainties. So the power of this Bayesian approach, and within the Bayesian approach, relies on the correct propagation of a natural and correct propagation of all the uncertainties from the very beginning of the pipeline up to the very end of the pipeline, so the cosmological parameter estimation. So just summarizing what we discussed here, is that we estimated cosmological parameters within a global Bayesian analysis framework. We implemented two likelihoods, a low-L pixel base for both temperature polarization and a Gaussianized Blackwell based one for higher TT multiples, and show the impact of marginalizing over model parameters in terms of tau posterior distribution. But it's just a benchmark, as I said, tau. So what was the point? The point was to show how methodology can work. So our methodology can provide cosmological parameter estimates. This is perfectly doable, but also, and maybe the real focus is this one, is that we can do this correctly propagating model parameters and certainties throughout the pipeline. So I want to thank all the people that worked in this project with me, and also want to thank European Union for giving us money. So if there is any question, this is the time. This is the moment for asking. Thank you.
Thank you, Simone.